So this is the session 3 for the model 2 of the response spectrum. Here in the last session you have seen about the free vibration of the single degree of the freedom. So in continuation of the free vibration for the single degree of session, here you will going to study the free damped vibrations of a single degree of a freedom of a system. You can see that from this equation, whatever it is there, and the free body diagram, the whatever the force is there, so it will be remain zero. So that is, since it is a free is there and rest of the other things are present, that is the stiffness force is there, damping force is there, and inertia force is there. So that's why the equation 1 which is equal to 0. So here let us consider that x, you can take it as a into e raised to gamma t. Now you can substitute the corresponding the x dot as a delta exponential of lambda t, and similarly x double dot, that is acceleration, that is nothing but d square x by dt square, that is as a into delta square in lambda square into e into lambda t. So that you can put it in the equation number 1. So the equation number 1 will looks after putting the x dot as well as the stiffness k, whatever the k is there. Okay, so just divided it by m also. You can divide it by throughout the m also. So now further you can just take out the a into e raised to lambda t outside, and now the equations will become lambda square into lambda into c by m into k by m, it is there. So that is equal to 0. So as usual, the frequency is nothing but square root of k by m, and whatever the damping is there, damping force is there, so that you can put over here as a c by 2m. So now, so you just put it the corresponding values. The n is equal to c by m. You can just put it here n, as well as here the p, that is the frequency, actual frequency, you can substitute over here. So now in this whatever the equation was there, so you can find out the lambda, that is using the quadratic equation, that is the quadratic equation root 1 and root 2. So you can see here there are the two roots are there, lambda 1 and lambda 2. So these lambda 1 and lambda 2s are depending upon the whatever the n and p values, whatever the n and p values. So now here whatever the cases are there, so for the roots, so whatever the damping ratios are there, so damping here, the damping ratio is depending upon the three cases. The first one is the case 1, where n is greater than the p, that is the natural frequency. So here in this case, the lambda 1, lambda 2 both are the negative, both are negative, but they are real, they are real. So that's why the root of the equations will be the positive only. So that's why so we can just see here that the x, whatever the displacement equation is there, you can put it a1 and a2 values and the corresponding the root values. So now this lambda 1 and lambda 2s are negative, which implies that motion decays exponentially with the time. Hence in such these cases there is no the whatever the period this one periodicity, that is, or non-harmonic motion, but the damping is so huge that the system just come slowly to the equilibrium from the displaced position. You can see that the overdamped cases, the how this the decay of the curves of the displacement will take place with respect to time is concerned. Now the second case, an is equal to p. So n is equal to p. So under such cases, the roots, whatever it is there, so in the equation, the square root term will vanishes, and the lambda 1, lambda 2, whatever it is there, so they are negative and equal. So that's why the root of equation x is equal to a1 into lambda t plus a2 into e raised to lambda t. So whatever it is there in the equation number 6. So this particular case is called as critically damped. This critical. So what is a critical damping? The damping in which there is enough to bring it back to the equilibrium position. So you can see the decay curve, how it will be there. So directly it is come back to the original positions. Then according to that, since n is equal to p and c divided by 2m is equal to p, that's why c is equal to 2 times of mp. So now the next case is the third case. So there are three cases will be happens in the pre-damped vibrations. The third case, whatever it is there, so under such cases it says that n is less than p, and here n is less than p in the sun terms, the whatever the square roots are there, so they are become under square root will become the conjugate roots. Why it is conjugates? Because it is a p is less as compared to this one, so that's why square root minus will be the conjugative root. So that is the two roots, lambda 1 and lambda 2, and whatever the equation is there of the motion, we can put it as a e raised to lambda 1 and lambda 2. So like that, the two terms we can put over here, or you can simplify further and put it x is equal to, take it e raised to nt outside. So here a1 and a2 terms are there, you can see the lambda 1 and lambda 2 for the e raised to values are there. So now since e raised to whatever plus or minus the whatever the t I and t is there, so here you can have the simplification in terms of the, we can write down in terms of sine and cos terms. So same thing you can write down as cos function as well as the sine function. So now you can substitute the same thing in this above equations. So in this above equations, you will be having after putting the some the boundary conditions at t is equal to 0, at t is equal to 0, what will happen? So here we will be having c1 is equal to a1 plus a2 and c2 is equal to I times of a1 minus a2. So now c1 and c2s are calculated, so that that we can put over here as a1 plus a2 as c1 and a2 minus a1 as c2. So that is the equation number c1. So now the c1 at t is equal to 0, at t is equal to 0 and x is equal to x naught, the whatever the velocity is equal to x dot, so velocity will be the x dot, and these conditions of c1 and c2s are there, so they are to be computed. So now c1 and c2s are to be substituted at the corresponding x dot values as well as the x values. So now after simplifications, you will be having c2 is equal to this much value, whatever x dot plus n x dot square root divided by square root of p square minus n square is equal to c2. So now you can substitute the c1 is equal to 0 here at that point, and from x2 point x naught dot you will be having c2 value. So both the c1 and c2 you can put it, and now it will become the equation number 8. The equation number 8 is describe the motion of undamped cases. So now all these three cases, if you will put it in a single this one response, that is x versus the displacement versus the time. So here you will find it the over damped cases whatever it is there, and the critical damped cases here, and the remaining whatever it is a under damped cases, and most of the civil engineering structures will be of under damped only, and whatever the under damped cases is there, so like that the under damped vibrations will takes place. So that is the how one can get the informations about the amplitude of the vibrations, how it will going to decay. Now let us take some numerical examples so that you will come to know that how one can find out the numerical examples can be solved from this topic. So here it is that a platform of weight 18 kilonewton is being supported by the 4 equal columns which are clamped to the foundation, and experimentally it has been computed that since the static force is there, 5 kilonewton is applied horizontally to the platform, produces the displacement of 2.5 mm. It is estimated that the damping in the structure is of order 5% of the critical damping. Compute only first one, the undamped frequency, second is damping coefficient, third is logarithm decrement, as well as the number of cycles at the time required to amplitude of the motion required to be the initial values of 2.5 mm to 0.5 mm. So here before going to this one, so it's better to take out this logarithmic decrement topic. So here in this logarithm decrement topic, we can see that whatever the undamped cases is there, gradually it is going to be come down. So for the free vibration under the damped the single degree of freedom, the oscillatory motion which is shown in this figure, what will happen with increase in the time, there is a the gradual decrease in the amplitude. You can see that gradually the amplitudes are decreases. The whatever the delay in the amplitude is expressed by the logarithmic decrement. So whatever this decrement is there, gradual decrement, it is called as a logarithmic decrement. And here the delay in the amplitude is expressed by the this logarithmic decrement, so that you can see it. Now the whatever the natural logarithm of the ratio of two consecutive peaks are there, x1 and x2, so this one is to be expressed as delta. Delta is the logarithmic decrement, and this one is expressed as log, natural log ln. This is ln of two successive ratios, x1 and x2. x1 is amplitude at the first point and x2 is the amplitude at the second. Two successive the points are there. So that is the way how this logarithmic decrement can be studied. So here how it is arrived is very simple. So at any instant time t1, and x1 is given by whatever the previous the case is there, so the displacement equation, as well as x2 at the next time, x2 will be the next amplitude occurs at t2 plus t, means again the time period is added. So to whatever the consecutive peaks are there, so that one will be put one over the other, no, means whatever the equations are there, just divide one, and here the whatever the natural logarithm is there, x1 by x2 is to be put in the side, and here that is nothing but delta is the natural logarithm, and simplifications you will be having 2 pi n divided by square root of p square minus n square, it is there. So now you can just again simplify by divided by p square, so that you will be having whatever the n by p is there, so you can say that it is the damping ratio. So this one is nothing but the damping ratio, and delta is equal to 2 pi chi into 1 square root of 1 minus chan square. So here chi is nothing but the damping ratio is a very small, and in that cases delta is equal to 2 m. So therefore chi you can put it as 1 by 2 pi into ln. Ln means natural log ratio of x1 by x2. So the damping ratio can be calculated if the two successive amplitudes are known to you. So like that the problems is to be solved. Now go back to the example number 1. So here from this example, so whatever the stiffness force is there, it's given as the 5 kilonewton is there. 5 kilonewton divided by the displacement is 2.5 mm is there, so much of Newton per mm. and whatever the natural frequency is square root of k by m. Now you substitute k as well as the m is the mass. So here mass is given as the 18 kilonewton is there, 18 into 10 raised to 3. So just make it this one, and this whatever the k is there, and m is there, so just divided by 9.81. so here we will be having natural frequency so many radians per second, the first one, and the critical coefficient, that is the cc is there. Critical damping coefficient is equal to 2 into square root of k into em. So that one will be is equal to 2 into k is there, as well as m here means w by g only. M is equal to w by g. Here also whatever the m is there, so w divided by g, that one is made. So according to that, the critical coefficient of the damping is 121.16 newton second per mm. And since actual damping whatever it is there, so it's a 5% of the critical damping, means 5% of cc. 5% of critical damping means 5 by 100. So actual damping is 6.06 newton second per mm. So like that the example is evaluated. Now let us take the another example, that is example number 2. So in this example, let us see that the whatever the vibrating system is there, it's consisting of the weights 50 newton and a spring with the stiffness of 4 newton per mm is viscously damped. The ratio of two successive amplitude is 1 is to 0.85. Compute number 1, the natural frequency, logarithm decrement, damping ratio, and damping coefficient, and damped natural frequency. So now let us see it one by one. So here whatever the natural frequency is obviously square root of k by m, and mass it will be there in terms of weight, so that is the weight divided by g. G is 9810, so much of mm per centimeter square. So now you just k is equal to is given 4 newton per mm. So the natural frequency is equal to k by m is there. You substitute k by m, so that you will get so many radians per second. And the frequency, you will, if you want the cycle cps cycles per second, then if you have to natural frequency divided by 2 pi is there, so you will get 4.46. now logarithm decrement means the two successive ratios is there. Okay, so natural log, this ln, it is a ln means natural log. So natural log of x1 by x2, x1 by x2 ratio is given as 1 is to 0.0. so first x1 is 1 and 0.85 is x2. So now the logarithmic decrement is also calculated. Once the logarithm decrement is calculated, now damping ratio xi is to be calculated using the ratio delta is equal to 2 pi xi, or xi is equal to delta divided by 2 pi. Delta is known, so logarithm decrement, so logarithm decrement divided by 2 pi, so that you will going to get damping ratio as 0.026. Now what is the damping coefficient? So damping coefficient is to be calculated using the relation xi is equal to c divided by 2 into square root of km, or 2c is equal to 2 xi into square root of km. So now substitute xi, damping ratio is known, k is known, as well as m means w by g, that is also known. So directly you will get so many newton second per mm. Then what is the natural frequency damped? It is damped natural frequency. Natural frequency is known. Now damped natural frequency is equal to, that is PD, that is a damped natural frequency is equal to natural frequency into square root of 1 minus xi square. So xi square means damping ratio is there, P is there, that is natural frequency. So that damped natural frequency PD is nothing but 28 radians per second. So this is the other example. Now let us take the next example, which is gives that a one-story building is idealized as a rigid girder having the total weight W and the weightless columns. Okay, during the jacking operation while carrying out the free vibration test, a horizontal force of 100 kilonewton displaces the girder laterally by 0.5 centimeter. After instantaneous release of the whatever the initial displacement, the maximum displacement at the end of first cycle is noticed as 0.4 centimeter, and then the time period which is required for this action is 1.4 second. Then determine number 1 the effective weight W of the girder, undamped frequency of the vibration, and then the damping coefficient and the amplitude after the 5 cycles it is there. So now let us see that this is a building, one story building is there, weight is there, the stiffnesses are given k by 2 k by 2, that is the stiffnesses, and this is the damping, how this and here the jacking force is applied, and suddenly it is released. So then this is going to vibrate freely. Okay, so here the force of 100 kilonewton is produces the displacement of 5 centimeter, means 0.5 centimeter, means 0.005 meter. Now the static displacement is 0.005 meter. Hence the equivalent stiffness is given by, stiffness is nothing but force divided by displacement, force divided by static displacement. So stiffness is equal to force is 100 kilonewton is there. So now divided by the displacement, so that we will going to get so much of kilonewton per meter, or you can convert in terms of newton per meter the stiffness. And for the cases whatever it is there, so here the whatever the time period is there, so time period is 1.4 second, that is given, 1.4 second is the time that is given to us. So now you just see that once t is known, so the frequency is nothing but 1 by t, so that you will going to get 0.714 so much of cycles per second, or the natural frequency is also known as the omega n. So that is nothing but 2 into pi whatever the f is there, 2 pi f. So here f is known as 0.714, substitute here, so that you will going to get the natural frequency as 4.486 so much of radians per second, so much of radians per second, or this one can be also written as square root of k by m. Now once you know the frequency as 0.714 cycles per second, nothing but the natural frequency is 4.486 radians per second, so that is square root of k by m. Omega n is equal to square root of k by m, or p, omega n or p, so it will be denoted as either p or omega n, both are same. And then now let us put it the k by m, you just take it the square root, means square it, omega n square it, and you can say that it is 20.214 times of the whatever the m is there, m. So here it is given as the whatever the value is there. Okay, so the k is there, so now m is equal to, so m is equal to this particular value. Okay, k divided by the 4.48 square is there. Okay, that is 20.24. so that's why m is equal to k divided by 4.48 square, that is 20.124. so now mass is nothing but 993838.2, that much of the kg mass can be calculated. Now effective weight of the girder is nothing but, weight is equal to nothing but mass into g. So here g you can put it 9.81, and mass it is in terms of kg, directly you will get so much of newton, or you can convert it in terms of kilonewton also, that is 9749.5. And now next one is the damping coefficient calculation. So damping coefficient calculation means cc is nothing but 2 into square root of k into m is there. K is also known, m is also known, substitute over here, so directly you will get cc is equal to so much of newton second per meter, or you can convert in terms of kilonewton second meter also, that is 8916.7. Now here it is given that two consecutive amplitudes are there. One is 0.5 centimeter initially, and later on it is taken it as 0.4 is there. So now you can find out the whatever the logarithm decrement as the delta is equal to natural log of the first amplitude to the second amplitude, that is AK divided by AK plus 1 is there. So that ratio is 1.25. 0.5 divided by 0.5, that ratio is 1.25 is there. 25 is there. So now you will going to get that one is nothing but equivalent to 2 pi xi, 2 pi xi. So now if you know that 2 pi xi, now the damping ratio can be easily calculated as the whatever the values of 0.223 is there divided by 2 pi, you just divide it, so that damping ratio is 0.0355. Now the damping coefficient is nothing but Cc into Xi. So already Cc is known, Xi also is known. So now substitute over here, so that you will get 316.54 kilonewton second per meter. Now after first 5 cycles, what will be the amplitude? What will be the amplitude? So for that there is a one condition is that whatever the successive ratios, initial as well as n means after 5 cycles, so that is nothing but e raised to n delta, or delta is equal to 1 divided by n into ln of n, means number of the cycle, whatever the factor n is there. So in the present case the n value whatever it is there. Okay, so now you just substitute here as the 5. So now you can substitute delta is equal to 1 by 5 and the whatever the ln of n it is there. So now inverse of n, so whatever it is there, number of cycles, n is equal to 3 cycle will be there, and the corresponding amplitude is equal to so whatever n that ratio is there, so whatever the n ratio is there, so a naught divided by n is there. So now the whatever the displacement will be takes place at the end of 5 cycle is 0.1645 centimeter is there, 1645 centimeter is there. So like that the whatever the amplitude at the end of 5 cycle is calculated. Now the next problem is that a platform weighing 7 into 10 raised to 2 kilonewton is supported 4 columns. The column is identical and have clamped the both ends. It has been determined experimentally that the force of 1.7 into 10 raised to 5 Newton horizontally applied to the platform produces the displacement as 2.5 mm. The damping is 5% of the critical damping. Again it is asked to calculate undamped natural frequencies, absolute damping coefficient, logarithm decrement as the number of cycles, and the time required for the amplitude of the motion to reduce from 2.54 to 0.254 mm. Now let us take one by one how it is to be calculated. A force is there 1.75 into 10 raised to 5 and which produces the displacement of initially 2.54. So now the static displacement is 2.54 into 10 raised to minus 3 meter. So we can convert it meter. And now the displacement is known, force is also known. The stiffness can be equivalent, can be calculated. K is equal to stiffness, K is equal to force divided by the static displacement. So you substitute, so you will going to get it 6.9 into 10 raised to 7, so many Newton per meter. Now the weight of the platform is known to us as the 7 into 10 raised to 2 kilonewton is there. Make it Newton, convert it Newton, and hence the weight is known, so the mass can be easily calculated. Mass is equal to W divided by G, whatever W is there, just divided by 9.81, so that you will going to get so much of kg, that is 7.135 into 10 raised to 4 kgs is there. So now what is the natural frequency? Natural frequency is equal to square root of K by M, and this K is in terms of the so much of Newton per meter is there, and M is in terms of the kg. So then you will going to get the natural frequency as so much of radians per second, 31.09 radians per second, and also the whatever the unnatural frequency, that is Fn is there, so that is nothing but omega n divided by 2.5, so that you will get 4.94 cycles per second. W divided WN, natural frequency divided by 2 pi. Now the critical damping is nothing but Cc into 2 into square root of K and M. So K is known, M is also known, so that you will going to get 4437.6 Newton per second is it, make it kilonewton per second. Now damping ratio is given as 0.05% damping is there. 5% damping means damping ratio is equal to 5 divided by 100, that is 0.05 is there. Now the actual the whatever absolute damping coefficient is there, Cc is equal to C is equal to Cc into J, damping ratio. So now the whatever the damping ratio is also known, Cc is also known, both you multiply, so we will get C, that is damping coefficient is 221.9 kilonewton second per meter, and logarithm decrement is delta is equal to 2 pi by J. J is damping ratio is also known to us, so that logarithm decrement is known. Now here it is said that what will be the number of cycles. So here A0 by An is nothing but this one. They are like logarithm decrement delta is equal to 1 by n into natural log of n. So here at present the whatever the A0 is there, that is initially is 2.5 and reduced to the 0.25 mm is there. Both ratio is nothing but n value is 10. So now logarithm decrement is equal to 1 by n, means number of the whatever the cycles are there, number of cycles are there. So that n is equal to 1 by delta into ln of n is there, that is a 10 is there. So now substitute delta, also substitute ln of n is 10 you substitute, so that you will get 7.33 cycles, 7.33 cycles. So this is all about the how the numerical examples as well as this one, the free damped vibration, free damped single degree of freedom. So free damping means the damping is there, but the vibration is free vibration. So like that you have seen both the theoretical expression as well as the meaning of the logarithm decrement, and the three cases that critical damping, over damping as well as under damping. So all the civil engineering structures are of under damping cases only, and the corresponding some numerical examples you have studied in this particular session. This is all about the topic of free damped vibrations of single degree of freedom of a system.